Fault data can also be gathered manually. This is done by checking and logging the operation of protective relays. As you know, each relay is equipped with a brightly colored target or flag that tells us when the relay has indeed operated. Such relay actions are always logged for future reference and analysis. Indeed, on distribution systems, this is often the only information which will be available to assist analysis. Here is one example of a relay action log which reports upon failure of a lightning arrestor during a lightning storm. The failed arrestor was located on the low voltage side of a 115 to 69 kV auto transformer. The resulting fault within the transformer's zone of protection caused the differential relay to operate. This in turn tripped all three breakers, primary, secondary, and tertiary, to completely isolate the fault. The actual information logged includes the date and time of the relay action, the numbers of the breakers involved, the relay targets, the time each breaker was closed, and the number of the pertinent oscillograph recording. In this particular case, the investigator, using all of the data along with the oscillograph traces, decided that all relay and breaker actions were correct. This is noted on the form. Any misoperations would typically be reported on a separate log, and a thorough investigation would follow. Of course, these relay action reporting procedures will vary from utility to utility, so you must be sure to check and learn your own company procedures. At this point, it's time for a break. In the next segment, we'll be looking at fault analysis tools in more detail. Until then, please switch off the videotape and review the written material in your workbook. In this segment, we'll be looking at the most common analysis tools which are used to investigate faults and other disturbances on the power system. These are oscillographs, system one-line diagrams, sequence of events recorders, relay targets, DC schematic diagrams. By correlating the one-line diagram with the oscillograph traces, we can usually reconstruct what happened and consequently analyze the fault. We may then verify our findings by checking the printout from a sequence of events recorder, also known as an SER. The SER may be an integral part of the oscillograph system, but quite often it is a standalone machine. This type of recorder is capable of monitoring 1,000 input points. For example, breaker open or closed status, breaker trip coil status, relay operations, transformer and generator alarms, and so on. The SER is constantly monitoring the status of each input point and prints out a detailed record whenever the status changes. A typical SER printout gives the exact time of the event down to the millisecond. It can distinguish between two events occurring 1 millisecond apart. It provides a plain language description of the event, the identification number of the input point, and an A or N code indicating whether the status of the device became abnormal or normal. In some installations, instead of a specific SER, the status is monitored by telemetering, that is, the SCADA system. Another tool we need to use in fault investigation is information regarding relay targets, which is usually logged by operators. Like the SER output, these logs are normally used to verify and support the conclusions drawn by examining the oscillograph records. However, in some cases, relay target and SER data have provided the missing link in solving problems due to disturbances. Now, let's take a closer look at the oscillograph machine. There are 4 oscillograph systems in widespread use on the power system today. These are referred to as quick start, pre-fault, continuous, and digital. The quick start oscillograph is the simplest type and uses a high-speed recorder. As soon as a fault is sensed by a protective relay or other sensor, the machine starts and the paper begins to move after 3 or 4 milliseconds. Of course, this presents a problem since the data at the very beginning of the fault is lost. The loss amounts to about 1/4 cycle of data. Also, there is no way of capturing the conditions on the system just prior to the fault. In spite of these disadvantages, many users prefer the quick start system. They are willing to live with some data loss in exchange for the simplicity of the machines. Another type of recording system uses a pre-fault oscillograph. This machine has a built-in solid-state memory that can store several cycles of data, up to 30 cycles in some machines. The memory works in a recirculating fashion. For example, at any instant in time, the memory stores the immediately preceding 30 cycles of data. As time goes on, the memory is constantly storing new data while dumping old data. But there's always 30 cycles of data in storage at any given time. Now, when a fault is sensed, the machine begins printing out the 30 cycles of pre-fault information it has stored in memory. While this is being recorded, the fault information is being inserted into memory. By the time the actual fault data starts recording, the machine is fully up to speed. This results in a very clear transition between no fault and fault conditions. Because of the recirculating memory, no data is lost. A third type of fault recording machine is the continuous oscillograph. In contrast to the quick start and pre-fault recorders, this machine does not need to be started by a fault or disturbance, and it also does not use paper. Instead, it continuously records system conditions on reusable magnetic tape. When a fault occurs, we can save about 6 hours of data by initiating a save command. This can be done automatically by protective relays or other sensors immediately after a fault is detected. Data can also be saved manually by a remote switch on the operator's console. Since data is continuously being recorded, the operator can decide to save information after the disturbance has occurred. Once the data is saved on magnetic tape, we can get a hard copy printout of the waveforms for analysis.